Okay, so in this module, let's talk more about the standard model operators of dimension 6. In particular, we're going to discuss the complete set of such operators, which include 59 operators when we consider baryon number. And so if we treat the standard model as an effective field theory, we can write its Lagrangian as a Taylor series with the dimension of the operators increasing. Dimension 6 corresponds to the second order terms here. And those are the terms we're going to talk about today. For further details about the analysis we'll discuss, you should look at this paper. So just to establish some notation, the lowest order standard model Lagrangian L0 is all the operators of dimension less than or equal to 4, and it consists of terms that can be divided into a gauge sector with the field strengths contracted, Higgs sector with the Higgs field H, terms for the fermions with the covariant derivative d slash, as well as the Yukawa interactions. In addition, we might consider right-handed neutrinos, but for simplicity, I'm leaving them out. And then there's also theta terms that involve contractions of the field strength and its dual field strength, where the dual is defined as an epsilon tensor contracted into the field strength. And I'm also going to not talk about those terms here, though we will include this dual field strength when we talk about the dimension 6 operators. So often, for the notation, often we'll suppress indices, but if we write them all out, then they would look as in this table. So for the gauge bosons, we have 3 different gauge bosons for SU3, SU2, and UU1. And there's 8 gluons and 3 electroweak gauge bosons, and then 1 gauge boson for hypercharge. I've listed the hypercharges of the various particles here. For the fermions, they come as left-handed, which are the L and the Q, as well as right-handed, the E, U, and D. And the left-handed guys are doublets under the SU2, so the J, little j index runs from 1 to 2. There's also this family index P that runs from 1 to 3 for all the fermions. Since the nature of left-handed and right-handed is always going to be obvious, we have a capital letter for the left-handed guys and a lowercase letter for the right-handed guys. I'll always suppress that index. And finally, we have the Higgs field, and it's a doublet under SU2, hypercharge a half. So when I want to be generic about the notation, I'll use this X for the gauge bosons when I mean any one of them. I'll use the fermion as psi and the scalar as phi. I also will make use of the fact that the 2 is a pseudo-real representation, so I can make operators out of H twiddle, which is an epsilon dotted into an H star. And in order to simplify the analysis, we'll use a Hermitian covariant derivative, d with a double arrow over top of it, which means d acting one way minus the d acting the other way. So these are our building blocks. We have the antisymmetric field strengths, the fermion field, the scalar, and a covariant derivatives. And since the power counting in this effective field theory is in operator dimension, we can list the dimension of these various objects, and if we want to build operators in L2, we just need to multiply these building blocks together to find operators of dimension 6. And when we do that, there are going to be various terms induced, and as we learned, you can use the equation of motion to reduce that operator basis. So in particular, if I write down all the equations of motion from L0, then they look as follows in this set of equations. And what they always do is they take terms with more derivatives and reduce them to terms with less derivatives. And so that's what how we'll use them when we consider reducing the operator basis. So covariant derivative on the field strength gluon field strength can be reduced to terms that involve fermions, etc. Here the field strength can be considered to have 2 derivatives. So here there's a term with a Higgs field, but only with 1 derivative. And likewise, for the fermions, we can get rid of d slashes, and for the Higgs field, we can get rid of d squared h. Okay, so those are the basic rules. We have to construct dimension 6 operators. They should be gauge invariant. We don't want to break gauge invariant with the dimension 6 operators, and Lorentz invariant. So we have to contract the indices in an appropriate way. So for example, if we take 3 copies of the field strength x, then the indices are antisymmetric, and we have to contract them up into this x cubed class, etc. for the other classes. Now, if you consider these different classes, I've color-coded them in red and blue, and what that means is you can see that the blue classes involve more covariant derivatives, And those terms actually can be removed completely by using the equations of motion and integration by parts. So there won't be any operators left over in the blue classes. They can all be reduced into the red class. The operators in the red class will contribute, and sometimes they can also be simplified. The number of such operators can be simplified using the equations of motion. So these are the various structure of the terms we can get for bosons. If we have two fermions, then we can either have a vector, scalar, or tensor current. Remember that the left and right-handed nature of the fermions is being suppressed in this notation here. And then we just have to contract with some object that has either one vector index, no vector indices, or two, and that gives these terms in the curly braces. And then finally there's the four fermion operators, and again we can put various spin structures between the fermions. So let me give you an example of using the equations of motion. So we made this class phi squared d to the fourth blue, and that means we can remove it completely. Let me show you how that works. So there's two fields here, phi, and the d's either act on one or the other, and those phi's are h's. So let's integrate by parts so that all the d's act on the h and none of them on the h dagger. Then we have an operator that looks like this with three d's. And we have to contract up those d's in some way. Well, we could contract them with an epsilon tensor, but that anti-symmetrizes the d's, and so then they become, the commutator of two d's is an x, and so that reduces us to the class phi squared x squared. We could also contract the d's with a g. For example, if we took g alpha beta, we'd have d squared h, but that d squared h can be removed with the equation of motion. Or we could have something like d nu d beta, with nu and beta contracted, g nu beta. In that case, we can't just use the equation of motion, because there's this d alpha sitting in between, but we can write it as a commutator, which is again an x, plus a term that's d squared h. And so again, those terms can be eliminated as well. It doesn't matter how the d's are contracted, we can get rid of all of them. And that's how this class phi squared d to the 4 goes away. Let's consider another class, phi 4 d squared. Here, all the operators won't go away, but we can simplify how many there are by, again, using the same type of tricks. So first, let's think about having two of the d's on the same field. Well, then again, we use the equation of motion to get rid of d squared h. Okay, so we better have the d's on a different field. What if both the d's were on an h dagger, or both the d's were on an h? In that case, I'm going to integrate by parts so that at least one of the d's is on an h and one of the d's is on an h dagger. So if I integrate this guy by parts, the d will move to the other h's. One of the terms will have a d squared h dagger, and that I can get rid of by the equation of motion, and then the other two terms will have d's on h's, and those I keep. So finally, we're left with one d on an h dagger, one d on an h, and then an h and an h dagger that don't have d's on them. And there's only two such operators that we can construct, which are shown in magenta here, two distinct operators. You might think that there could be more, because you could, for example, take the sigma tensor, the sigma matrix in the SU2 and make an operator like this one, but then that can be removed by a Fiertz identity and written in terms of these magenta operators. The standard basis when we count the 59 operators that people use is not quite the one that I show in magenta, so that the final answer is that there's two, but people use the ones I show here in red. So it's, one of them's the same, and the other one just has a partial squared with h dagger h. And that's equivalent to the operators we have up there, because if you let the partial act on the h's, h dagger h is gauge invariant, and so you can write it inside with covariant derivatives, and then taking the second derivative inside, you get a term from the cross terms where you have d h dagger dh, and that's this operator up here. And then you have terms with two d's acting on the h, which again can be reduced using the equation of motion to other classes. Okay, so the final answer for this phi 4 d squared class is that there's just two operators. And so that basically gives you an idea of the kind of techniques that we would use to reduce all of the operators. And we would apply similar techniques to all the different classes, and that would allow us to count how many operators we have. And that gives the results that I show in the table here. So I'm showing you the bosonic and the operators that are purely bosonic, as well as the operators that have two fermions. For this class x cubed, because of the antisymmetric nature of the indices, the vector indices in the g's, we have to end up contracting with an antisymmetric color or SU2 tensor. And then there's just these 4 combinations. And again, with the different duals, there's only one possible dual, because if we have 2 epsilons contracted, we can reduce that to g's. These are the 2 operators we talked about in this H4 d squared class. And then in the other classes, I get the operators that I show in the table here. So there's, in the end, 15 different bosonic operators and 19 operators that have 2 fermions, not counting the possible the family indices here on the fermions. And then there's the 4 fermion operators where we don't have any use of the equation of motion. We just have to enumerate the distinct combinations. We can still make use of Fierz identities. And so I've organized them here as left and right-handed classes. And so the left-handed class are always the capital letters. The right-handed guys are always the lowercase letters. And we just have these operators that I show here. And there's 25 of them. So if we count the 25 plus the 15 plus the 19, that gives the 15 operators total, as promised. So how would we make use of this? Well, if you think about what new physics means physics beyond the standard model Lagrangian L0. So that would appear as non-zero coefficients for these dimension 6 operators. And generically, if you write down a new physics model and you think about the new physics scale being much larger than the physics scale in the standard model, so the scale of the cutoff lambda is much greater than the mass of the W, Z, top, etc., then what we would find is just that generically we'd get non-zero coefficients for the dimension 6 operators. And what experiments do that search for new physics, if we haven't found it and we assume it's heavy, is you can just put constraints on the coefficients of these dimension 6 operators, for example. So let me give you a kind of timely example of that with the search for new physics in Higgs to gamma gamma at the LHC, which is being carried out both at CMS and Atlas. And this is a very interesting process. So the Higgs boson was discovered, and now we can look for new physics in Higgs decays. In the standard model, Higgs to gamma gamma only occurs through loops with the L0, and the dominant contribution comes from a top quark loop like this. Whereas in our our dimension 6 operators, we can actually have a tree-level contribution. And if we look at through the table and we determine which operators can give tree-level contributions, it's the ones I've put in a box here. So what happens is either B or W, because of the electroweak symmetry breaking, they both have a combination of the photon. It's a mixture of the 2. So either one of them can give a photon. One of the Higgs fields can be replaced by the vacuum expectation value of electroweak symmetry breaking, and then the other one by the dynamical Higgs field. And then we just take a photon out of each of the field strengths, and we have an operator that takes us from Higgs to gamma gamma. So let me write the set of those operators down and define some dimensionless Wilson coefficients C, and I'll use some obvious notation where I just label them by the same way as I label the operators. I've pulled out the dimensional cutoff lambda and used a common one for all the different operators, and I've also, for simplicity, pulled out some factors of the couplings, where the couplings that I'm pulling out correspond to the corresponding field strengths. So G1 for the B and G2 for the W. Then if I want to figure out how these operators contribute to the decay rate, I can conveniently write it as the decay rate for Higgs to gamma gamma divided by the result if you just had L0, which I'll call the standard model result. So that's the one term here is the standard model. Now for the operators here, OHB, OHWB, as well as OHW, these operators can interfere with the standard model. So this is a quantum interference, and I actually add them at the amplitude level and then take the modulus squared. The operators with the tilde here have the opposite parity, and so they can't interfere with the standard model result, and so they just come in separately. And that's what the terms here are denoting. So C gamma gamma denotes those 3 guys that can interfere, and C tilde gamma gamma denotes the 3 guys that can't interfere. So in terms of dimensions, our L2 operators have a 1 over lambda squared, which is appearing here explicitly in the terms C gamma gamma and C gamma gamma tilde. And the dimensions are made up by V squared in the numerator, where V is the vacuum expectation value. And then finally, we have the I gamma gamma, which is the loop suppression factor in the standard model. And that's showing up in the denominator here in the new physics contribution because it really shows up over here and we divided by it. Okay, so this is the structure of the contributions from new physics with this analysis in terms of dimension 6 operators. And then experimentally, we would put constraints on C gamma gamma and C gamma gamma tilde. And so the moral of the story here is that this is a useful framework for thinking about new physics. And generically, when we consider some process, we have 59 operators, but only a smaller subset of them will contribute to that process. Here in this example, there were 6. Okay, so that's it for today.